Welcome back. Traditional power grids keep the lights on by adjusting power plants to match whatever we are consuming. Demand response takes the exact opposite approach. When the grid is stressed, it asks buildings to reduce their demand to match the available supply. But how does a grid operator actually tell an entire office building's equipment to use less power? This diagram shows the pipeline. A grid operator uses OpenADR to send signals through an aggregator to a building energy management system. Because internal equipment relies on localized protocols like BACnet or Modbus, this external OpenADR signal must be translated. That makes the building energy management system the crucial translator. It receives the external economic request from the grid, decides what internal adjustments are safe to make, and issues the mechanical commands to the hardware to actually reduce the load. Grid-scale energy storage adds an entirely different tool to this system. Storage is unique because it can both absorb extra electricity when there is a surplus and release it back when there is a deficit. To deploy it effectively, you have to follow a strict engineering rule. You must match the physical duration of the storage to the specific duty it needs to perform. This chart maps storage response speed against discharge duration. Flywheels react in milliseconds. Lithium-ion provides hour-long bursts. Flow batteries offer longer shifts, while pumped hydro handles multi-day capacity. For question 11, fixing frequency drifts within seconds requires looking at how fast equipment delivers power. It is easy to select a 12-hour lithium-ion battery here simply because it holds more energy. That is a trap. High capacity is completely useless if the system cannot physically deliver the power fast enough to stabilize the frequency. Flywheels are the correct answer because they are specifically built for extremely fast, short-duration responses. In energy storage, a larger capacity battery does not make it universally better. The physical response time dictates the technology's viable use case. When a facility successfully reduces its load during a demand response event, the utility pays them. But paying a building for electricity that was never consumed creates a verification problem. The grid operator solves this trust issue mathematically by calculating a baseline. This graph compares an event day's building demand to a normal day. The baseline estimates normal usage by averaging recent non-event days, adjusted for weather. Financial credit is based entirely on the vertical gap between that theoretical baseline and the actual metered usage. Facilities often use large enterprise batteries to create that gap. Because a single revenue stream rarely covers the heavy capital cost, facility managers must stack purposes. The same battery might provide emergency backup power, monthly peak billing reduction, and demand response. Stacking purposes introduces operational risk. Capacity is a shared, finite resource. If you completely drain the battery to earn a payment during a scheduled demand response event, and an actual blackout hits the grid 10 minutes later, the facility is left entirely exposed. Participating in these programs requires balancing the theoretical financial earnings against very real-world operational vulnerabilities. Let's look at question 12, where a warehouse must choose the primary role for a new battery. It is tempting to choose demand response simply because it carries environmental value. You must look at the financial reality. Cutting a substantial amount from the electricity bill every month delivers a mathematically larger ongoing benefit. For question 13, shutting down supermarket refrigeration completely ruins frozen inventory. The operationally viable answer is to cycle the refrigeration. Here is an active recall test. Question 14 describes a university with an older BACnet system that wants to join an OpenADR program. Should they replace the whole system, respond manually, or install a gateway translator? Pause the video here and lock in your answer. Welcome back. The correct choice is installing a gateway. Do not fall into the trap of assuming older IT setups are dead ends. A gateway perfectly balances cost and reliability. It preserves the legacy BACnet investment while adding the necessary OpenADR translation layer needed to talk to the grid. Modern building integration relies on clever middleware to bridge legacy BAC systems with these new demand response requirements. Let's lock in the core rules for your exam. 1. OpenADR is the external grid protocol, while BACnet and Modbus control the internal hardware. 2. In energy storage, always match the battery's physical duration to its required grid duty. 3. Stack your battery revenue streams, but always protect your backup reserves. You've got a strong handle on demand response and storage economics. In the next module, we take these concepts inside the facility. We will break down building automation and smart city platforms, exploring how control loops, occupancy sensors, and a 4-layer IT architecture keep these complex systems running. Digital intelligence for sustainability hinges on the precise choreography of data pipelines to balance human comfort with the survival of the grid. See you in the next video.